In 1895, Albert Einstein started to think about traveling at the speed of light and observing a beam of light. He needed 10 years to find an answer and 3 weeks to write his famous paper. He described a flat, four-dimensional spacetime. In 1907, he realized that a person in free fall in a lift would experience being in an inertial frame. He realized of the principle of equivalence that says that a uniform gravitational field is the same as a uniform acceleration. He visualized the universe as a four-dimensional spacetime that curves under the action of gravity. It was the general theory of relativity. Imagine that you travel in free fall in the gravitational field of the Earth. You lose potential energy and you gain kinetic energy. In your free fall, you pass by two clocks at two different heights, clock 1 and clock 2. In your fall, you measure the time rate of clock 2 and then that of clock 1. Because you are moving, there is time dilation that you measure. If d tau 2 is the time rate of clock 2, d tau 1 is the time rate of clock 1, dt1 is the time rate of your clock, and dt2 is the time rate of your clock at 2. Then we have that dt2 is gamma d tau 2 and dt1 is gamma d tau 1. We can divide one over the other and get that the ratio of the times of the fixed clocks 1 and 2 is this expression here. In your free fall, energy, kinetic plus potential, is conserved. Because we are near the surface of the Earth and the speeds are not too high, we can approximate the kinetic energy by 1/2 mv squared. We can also expand Bayes' series of Taylor and substitute the velocity in this expression in terms of the potential energy. So we have that the rate of time of the fixed clocks depend on the gravitational potential. There is time dilation due to gravitation. Remember when we talked about the GPS and we mentioned that there is an effect due to velocity of the satellites but also another effect due to gravity? This is the gravitational effect on clocks, on the passage of time. The flat, four-dimensional spacetime of a special relativity is a particular case of the more general curved spacetime of general relativity. The spacetime interval ds is now written as a more general way as where these coefficients depend on the mass distribution. It is mass that curves spacetime. As a matter of fact, there can be cross terms, not just dt dt or dx dx and so on. We can have dt dx, dx dy, and so on. These are the components of a 4x4 tensor that describes spacetime. This spacetime tensor for a spheric uniform distribution of mass, like for example the Earth, is given by this expression. It is a diagonal tensor, that is why we don't have the crossed terms here. For a clock at rest at the distance r of the center of the Earth, dx, dy, and dz are 0, and d tau is equal to the square root of 1 minus 2gm over rc squared dt. This tensor that describes the geometry of a spacetime can be very complicated depending on the mass distribution that you have. Some simple distributions can be solved analytically, but most of them have to be solved numerically. This leads to surprising results such as black holes, gravitational lensing, expanding universe, which are studied by general relativity, and it's out of the scope of these lessons. This was just a taste of what's next after special relativity. Keep thinking four-dimensionally and may the science be with you.